So the linear regression model with k independent variables. With k independent variables is given by this. So the x1, x2, up to sk are the independent variables, while the dependent variable is a y. Then the alpha, beta 1, beta 2, up to beta k, this beta 1 is supposed to be beta k, are called the parameters of the model, of the linear regression model. So when you see a cap on top of the y, then it's an estimate. The estimated value of y is given using the estimated value of alpha, beta 1, up to beta k. So beta, this one is beta k cap. So when you say a cap, it means an estimate of the actual value, which is not known. So that is the linear regression model. So what are the assumptions for every model has got an assumption? I've got assumptions. So what are the assumptions and how do you validate them in the regression model? First of all, the relationship between the independent variable and the dependent variable should be linear. So a linear relationship, and observations are assumed to be independent of each other. Then homoscedasticity, that the error and the residual have a constant variance across all levels of the independent variables. The residuals are assumed to have constant variance across all levels of the independent variables. Then we have the normality assumption of the residuals. The residuals are assumed to be normally distributed. Then there should be no multi-collinearity in the independent variables. That is, the independent variables should not be highly correlated. When they are highly correlated, then you can use what I was teaching you last time, the principal component analysis, to reduce the correlated variable into one variable. So no autocorrelation. So the residual are not correlated with each other, particularly in a time series data. They are not correlated with each other. So then we have the final correct model specification. So these are the assumptions for the linear regression. In this lecture, I'll be dwelling more on the assumptions for running the linear regression model. We've been doing it right from the undergraduate, second degree, and now. So usually people are not particular on the assumptions. So I'll be dwelling more on the assumptions in this lecture and how you can remedy them when there are violations. So when the linearity assumption of the regression model is violated, what do you do? How do you check for linearity in regression? You can do a scatter plot to check whether there's a linear relation between the dependent and the independent variables. And when there's none, you can apply transformation. When there's a violation, you can apply transformation, either logarithmic transformation, square root, or etc. to remedy that violation. Or consider adding some interaction term. Then there's violation of independence, and then you can use a time series. We're looking at time series maybe next week or our next lecture. Time series, we'll look at that. That's when you are looking at longitudinal data instead of cross-sectional data. So linear regression is for cross-sectional data, while time series is for longitudinal data. Then panel data analysis of both longitudinal and cross-sectional. So when you violate the homoscedasticity assumption, what do? You use robust standard error or weighted least squared regression to account for the heteroscedasticity in your data. Violation of normality, you can use a QQ plot or do a normality check, Shapiro-Wilks test, to test for normality. So when there's no normality, sometimes you can apply transformation in order to resolve that, or use a non-parametric method if normality cannot be achieved. And violation of no multi-collinearity. That's when there's multi-collinearity. First, you use the variance inflation factor, the VIF, to determine if there's a multi-collinearity. If there is, then you can either remove the variables, maybe if two variables are highly correlated, you can remove one of them, or use a principal component analysis to reduce the dimensionality of your data. So that's when there's multi-collinearity in your data set among the independent variables. So the violation of no autocorrelation, that's when there's autocorrelation. You can use the Darwin-Watson test to test whether there's autocorrelation. If there's autocorrelation, then you can use time series approach, which we'll be looking at in our next lecture, time series. Please, how I made myself clear. Violation of correct model specification.
Example 8.1. A bank is analyzing the relationship between the size of loans disbursed in $10,000 increments and the corresponding profit generated in $1,000. Data from 200 loan transactions have been collected. The bank suspects that the relationship between loan size and profits may not be linear, especially for large loans where profit growth might plateau due to higher risk and diminishing returns.
Good. So the bank suspects that the relation between the two, the dependent and independent variable, may not be linear. And that is common with financial data. Sometimes the higher you go, there is something we call the law of diminishing returns. So the thing becomes flattened at the top. That's it comes to a time, though the independent variable is increasing, the dependent variable is not increasing much. So it means there is a diminishing return on your investment. So when it comes to such situation, you need to transform the data. Otherwise, when you apply the linear regression directly, it may not work. But let's look at the data. First of all, let's look at the data. But I'm going to cut and paste. Can you see my screen? My spreadsheet?
Yes, Doc.
Yes, please.
Okay. So I'll paste special. Then treat first row as variable names. Then you click OK, and everything comes. So let's go to data, under data variable manager to work on the names. So the first thing they say we should do is to visualize our dependent and independent variable in the scatter plot. So that's the first thing. Then you also say we should plot the residuals and etc. Why do we need a scatter plot? You want to see whether there's a linearity assumption. So when the y and the x are not linearly related, then it means we need to transform the data. So that's the first thing we have to do. Then we determine the optimal model. So let's start with the visualization. So you type two-way scatter plot profit. Profit is the dependent variable and loan size is the independent variable. So you type two-way scatter. So that's a scatter plot. Doesn't work, I'll stop teaching. Can you see my graph on the screen?
It worked now.
Can you see my graph on the screen?
Yes,
you
Doc.
can see.
Yes, Doc.
Great.
Yes.
Is it linear? Does not seem to be linear. The same plateau as you get to the upper. There's a sort of diminishing returns. As loan size increases, it comes to a time it's becoming like a flat something at the top. And that is common with financial data. Okay, it's very common with financial data. So this one needs a transformation. The relation between loan size and profit generated is not linear. It looks like logarithmic or quadratic or something,
Or exponential.
or exponential. Thank you. Who is that?
Silas.
Appears not to be linear. So
Yeah.
that's what I'll explain here. The graph is not linear. So we need to do a transformation. So I'll describe the graph here. There's some kind of diminishing returns as loan size increases. So when it's not always that when you have a data, then you do linear regression. People have been doing that a lot. If the data is not linear, the relation between the x and y are not linear, you need to do a transformation. So here, what transformation should we do?
Prof, will log work?
Yes, I still continue to try, but yes, we'll do a logarithmic, how do you call it? A logarithmic transformation. But first of all, let's run the regression. Though we know that will not work, we'll still run the regression and see that the regression of profit and loan size. So copy these two. That is if you want the BIC and the AIC. We use the AIC and BIC to compare models. And because we are going to compare models, after every regression model, you type E start IC, and that will give you the AICs and the BICs. Well, do this and paste it into your stata command. Make sure that the E starts AIC, shift it to the beginning if it has moved to the somewhere middle. Can you see my screen, my command window?
Yeah.
So the E start IC should be at the beginning. It should not be in the middle. If it's in the middle, shift it. So the command is this one, but because I want to compute the AIC and the BIC, you write E start, then IC, then the command. So the results come. I have the results on the screen. Can you see the results?
Yes, Doc.
So the AIC is 907.9889, and the BIC result is 914.5855. What do you use? You use to do comparison of models. The model with the smallest AIC and BIC is always the best. It's always the optimal model. So right now, this is our first model, but straight away we know that this model will not work because the relation between the x and the y is not linear. And because it's not linear, it's likely this model will not work. But we're still running for comparative purposes. And at PhD level, you need to run so many models and do a comparative analysis between the models and tell me which one is the optimal model. So that's exactly what we are doing. So we go back to our work. So we run that one. Then we also generate the residuals. You can generate the residuals. And using predict residual, reseed. So please, have you seen it?
Yeah.
Can you see what I've highlighted?
Yes, Doc.
So copy and paste it to generate the residuals. Paste it in your
Command.
stata command. What results here? There's no result, but if you want to see the residuals, the errors, you type edit and go back to your spreadsheet. You see that one more column has been added to the spreadsheet. Can you see that?
Yes, Prof.
Good. So these are the residuals, estimated residuals for your model. So every pair of variable has a residual. That's the estimated error term. So that is it. So we generated it. We are going to do a test based on that. And we are going to draw a graph also based on the residual. So that's why we generated it. So the next thing you do is to do a plot of the residual. You do a plot of the residual, and that's a command. So copy this and paste for the plot. Please, are you with me?
Yes,
Paste
Prof.
this command. Have you pasted it?
Yes, Prof.
So you get a graph similar to this one. Is your graph similar to what is displayed on the screen?
Yes.
Yes,
Okay,
please.
so what is wrong about this graph? What's the interpretation? Someone read very fast. I've written something on the screen. The interpretation of the graph.
The residual plot exhibits a clear systematic pattern rather than random dispersion around zero, suggesting a violation of the linearity assumption. This
Please, do you understand that statement? No, wait a minute. Do you understand that statement?
No.
Okay, let me explain. If there is a linear relationship between X and Y, this plot, can you see the screen? This plot will be scattered around zero, randomly around zero. But this is not the case. It started here and it's like parabola. It's like there's a pattern and it looks parabolic. It's not round. This is zero. This is a point zero. When these points are randomly scattered around zero, okay, then it means that there's a linear relationship between the X and the Y. Already, we have seen here that there is no linear relation. So this residual plot confirms that there is no linear relation. So you realize either there's a U-shape something. When you see U-shape appearing in your residual plot, then it all indicates a lack of linearity between your dependent and independent variable. Are we okay?
Yes, Prof.
So there's no linear relation between the dependent and the independent variable. That doesn't mean there's no relation. There's no linear relation, but there may be a relation. Like Salah said, there'll be a logarithmic relationship, or there'll be exponential relationship, or there'll be quadratic relationship. So with tests we may not know, but the relation between X and Y is not really linear. So you cannot continue to run this regression that you have done here to be wrong. Can we move on?
Yes,
so we move to the second part of our analysis. Because this thing was not linear, we decide to find logarithm of the loan size. We find the log. So we model profit against the natural logarithm of the loan size and see whether that will work for us. So that's the first one we have done here. So copy this command and everything, including the IC, if you have it. The command, this thing I sent to you, can be converted. It's editable, so you can convert it to Word if your PDF can do that. But the copying will be easy for you. So you copy this and paste it. So what's the first?
Copied.
Come again.
The one you sent can easily be copied.
Yes, the last one I sent can easily be copied. So you can copy it, then paste it in your command window. So it's doing three things at a go. What are they?
Generating the natural logarithm.
First, you generate the natural logarithm of the loan size. We call it ln_loan. Then number 2, you find the regression between profit and the natural logarithm of loan size. That's number 2. Then number 3, you generate the AIC and the BIC. So we are doing 3 things at the same time. That's why we have 3 lines. Please, do you understand what I'm trying to say?
Yes, please.
Great. Why are we finding the natural logarithm of the loan size? Who can tell me?
Prof, I believe is to check if after finding the natural log, there will be a linear relationship between the two.
Exactly so. Because the original variable, there was no linear relationship between the two. So now we are transforming the independent variable by finding the natural logarithm. So the first thing you do is to find the natural logarithm and generate a variable for that, calling ln underscore loan. Then we find the regression between the dependent variable and our new independent variable, which is the transform independent variable. Then you also compute the new AIC and BIC. Okay. Good. So another variable has been created. So we have 2 more variables, the residuals and the natural logarithm of loan has been created. So now we want to regress profit on what? On natural logarithm of loan. So that was the second command. Okay. So all of them have been created. When you go to the you go into the command window, you see the results. So these are the results for the regression that we did. So I want to do the second model. The second model is a log-log model. That's I'm doing so many models so that I can check which one has the lowest AIC and BIC. And the one with the lowest AIC, BIC is the optimal. Please, have I made myself clear?
Yes, Prof.
Great. So this time, I want to also find the logarithm of the profit. I want to find the natural logarithm of the profit and run the natural logarithm of the profit against the natural logarithm of the loan size. Okay? So you copy this, you paste. Then thirdly, we do a quadratic transformation. A quadratic transformation. So this is a quadratic regression. So what are we running? Profit as a dependent variable. Then we have beta naught, beta 1. So you have loan size, then we have loan size squared, then plus the error term. So how do you run it? So we regress.
Okay, sure.
So what's the command? First, what was the dependent variable? Profit?
Profit, yes.
What's the independent variable? Loan size. But loan size is quadratic. We are assuming loan size is quadratic. So first, you type loan size, then type C dot loan size, then hash C dot loan size. It means square. That's the mean. This one means loan size squared.
Oh, okay. Okay.
This whole command means loan size squared. So C dot loan size, then hash C dot loan size. It means loan size squared, this variable. So you have loan size and loan size squared in your model. So when you copy this and you paste, it to give you the results.
So, Prof, just a quick one, please. Is that the hash? Is that the multiplication for theta?
Yeah, that's how theta recognizes it in the regression model.
Oh, okay.
It's not multiplication for theta, but for the regression model, that's the way it reads the hash.
It.
That's how it recognizes the hash. But in general, it's not multiplication.
Okay.
Good. So we ran that one as well. We have the AIC and the BIC. I'm going to put all of them into one table, then we do a comparative analysis. So here we are. Please, can you see? So you have to summarize all the 3 models, all the 4 models in one table, because we want to compare them as to which one is the optimal. So first, we have the linear model. You look at the R squared, you can use the R squared, you can use the root mean squared. The model with the smallest root mean squared is better. A model with big root mean squared is not good. So which of the models here has the smallest root mean squared?
Log.
The
The
log
log
model.
model.
The log, where we transform the dependent and the independent variable. And also for the R squared, the model with the biggest R squared is the best. Which of the model gives us the biggest R squared?
Log. Still log.
And for the AIC, the model with the smallest AIC is the best. Which one top? It was still the log.
Log is in a
And the
comfortable
BIC,
zone.
the model with the smallest BIC is the best. Which one top?
Log.
It's still the log. So in all the departments of comparison, the log model is the optimal.
Doc, what can be said about the p-values? I see that all the p-values are
all the p-values are significant.
less than, they are,
all of them are less than. But the fact that you have a good p-value, that doesn't mean that your model is good. We have other ways of comparing models. These are the p-value associated to this f-stat. And all the p-values are saying that, when we are teaching the undergraduate, we say when you have a small p-value, it means your model is good. It's not always so. So we don't only use a p-value to justify the validity of your model. Please, do you understand?
Yes,
Yes,
sir.
sir.
Yes.
Great.
Yes, but can you please interpret statistics?
The f-stats, the direct because of the p-value, the f-stat is an alternative to the p-value. If I want to interpret this, then we need to read the F distribution table and do a comparison between the observed F value here and the critical F value read from the statistical table. But that can easily be done using the p-value. Since we have the p-value, I don't want to concentrate on the f-stats because the two will give you the same interpretation. Please, do you understand?
Prof.
Yes, I'm listening.
Is
Okay,
this
sir.
table that you generated, did you do it manually or there's a code for Stata to get it?
Come again.
The table that you have just displayed, is it something you did manually?
I did it manually.
Okay, thank you very much.
It's good to, but all these results were in what we ran in the Stata.
The various tests, then you have grouped it
The
together.
various tests we conducted, each of them, we did a AIC and a BIC. Each of them gave a root mean square. Check it. Root mean square values were there. Then the R squared also were there. So I don't know how to do it better than to do it manually. Maybe there's a way somebody can come out, the way you can generate it out of. But I did this one
I
manually
was thinking there may be an Excel command, or maybe I'll add Silas.
No, not yet. Not yet. Not yet. Maybe an alternative way is to copy the results, all the results of the four models, copy into any of the AI this thing, and tell AI that it should do a comparative analysis table using the R squared, root mean squared, AIC, BIC, F stars, and p-value. Maybe that can give you a table, a nice table like this. Now, because of technology, no need to suffer. Can we move on, please?
Yes,
Can
Prof.
we move on?
Yes, please.
So, which of the model is the best?
Log.
Which one is the optimal model? The log. That's what I've described here. So when you read the is a description of what I've written here. Means our optimal model is given by this. You read the value for beta naught in the log model was 1.36, while the gradient for the log model was 0.44. When you check the results, I think that was the last but one. model we run is 0.44. So this is our model. But why do we call this elasticity in regression analysis? Who can tell me? The log-log model is called elasticity in regression analysis. And the beta one is called the elasticity. That's the name given to it. That's when you run the log-log, not profit log. It should be log-log model. Since you are not answering me, let's continue. So you realize that when I plotted the log-log...
Oh, please, when it's less than 1.
Come again.
Please, is it when it's less than 1?
When what is less than 1?
The R square is less than 1.
The R squared is always less than 1. It's always between 0 and 1. For any model, R squared is always between 0 and 1. It cannot be more than 1. It cannot be less than 0.
I think the coefficient directly measures elasticity.
Exactly. That's the coefficient, the beta one. You know elasticity in economics. Elasticity in economics. So the beta one measures elasticity.
Something like gradient.
Yeah, it's a gradient, but the gradient is a measure. That's the log-log. It's only in the log-log model. The gradient is a measure of elasticity.
Yeah.
So when you come to the interpretation, you understand it better. When you are interpreting the coefficient. And this is a log linear model. Is it the log linear model was number 2? Was it number 2? In our comparison, the log linear.
It was number 2.
This one?
Number 2.
Yeah, number 2.
Yeah, it's number 2 when you are doing the, yeah. So you can either choose this one. They are both good. This one or the log linear model is also good. It's also good, but the best is the log model. It depends on your, how do you call it, your objectives. Sometimes you are interested, you are not interested in transforming, so they are both good. So this is a log-log regression model, and this is the log linear model. Log linear model where only the independent variable was transformed. And that one also gave us this specifications. Then we're asked to do business interpretation, implication, which I've also done clearly over here. So when you read, you understand.
So in a typical model as designed, we couldn't find linearity to enable us to do a regression analysis. And therefore, we did all these different models. What does that mean in respect of data that we collected and the model we have designed? Are we saying that our initial model is not correct and therefore we've generated something new models to work with? What is the practical implication? Anyone can help?
It's the assumptions. He was trying to let it comply with the assumptions of the linear regression model.
So to add to what my brother said earlier, the little that I know, who is there? So what I know is that normally when you collect data and we are talking about linear regression model, you know, every model comes with its assumptions. So when those assumptions are not met, then you have to make sure you run those things he did so that you pick the best which conforms to the assumptions that you made earlier.
Mm-hmm.
You understand, my brother?
Yes, but in terms of data, so are we tweaking the data?
So in terms of practical application, you are saying there is a linear relationship between so and so and so and so based on certain assumptions. So when you have the data, you know, data is not like, we don't have a situation where data will meet all assumptions.
Right.
but you still want to work with the data. You understand, my brother? So
Yes.
So if you are assuming that there is a linear relationship between them, but the raw data does not meet those assumptions, then you now have to manipulate the data by running the things he did. So that the one which conforms to which best conforms to the assumption, then you now use it. So you understand. So let's say the raw data might not be perfectly linear, but then the log of the data now meets those things.
Right.
Okay, so you look at, for instance, this is the raw data when we plotted. Is it linear? It's not.
It's not.
Because you realize the thing plateau at when it gets here, it's like curved. Are you saying it? But when we apply the logarithm to both, the log, look at it. Does it look linear? Yes.
Yes, it looks linear.
Can you see that when we plotted the log is now linear?
Yes,
So they will also give us the best model. We plotted it now, it is linear. It means we have now transformed the nonlinear data into linear. So now we can use linear regression to work it.
Yes, please.
And when your variables are not linear, you cannot run linear. That's why you call linear regression. Your variables, you have linear relationship.
Okay.
So with this and try and error, based on our first graph, number one, I realized that the first graph looked like quadratic. So I did a quadratic transformation. It also looks like logarithm. So I did logarithmic transformation. And the long run did a model comparison by comparing their R squared, root mean squared, AIC, BIC, and the p-values. All the p-values say significant, so I cannot rely on it. So the model with the smallest AIC or BIC is best based on model selection. And the model with the smallest root mean squared is also one of the best. So in all departments, it was a log model that topped. So we say that the log model is the optimal. Though the other models are also good, this one is okay. And the quadratic model also appears to be okay. But the optimal model is the log model. So we use that one.
Thank you very much.
Doc, so assuming none of the other method, maybe the log linear, didn't also
then
give
you
us a
have to
linear.
keep trying. That's why I plotted it first.
You have to keep trying.
That's why we plotted it first, to know the nature of the violation of the linearity. When you realize the nature of the violation, it looks like parabolic. There's a scatter plot here, it looks like parabolic. Then you know that it's likely to be quadratic. It could be exponential, it could be logarithmic. Usually logarithmic work with most of the models. So the first transformation you do is logarithmic model. First transform only the independent variable, then also transform both the independent and the dependent variables. Then you check and you do the model comparison and see which one fits better. So here our optimal model is the log model. Can we move on, please?
Yes.
Yeah, please, Doug. With the linear plot that you did for the log model, do we still use the two-way scatter plot?
Yes, you use that one.
Okay, but this time around,
plot, but your dependent variable should be ln profit. When you check, do you see the name we gave to when you go to the spreadsheet, it's called ln underscore profit. That's what you use for your dependent variable when you are plotting. Then use ln underscore loan as your independent variable. Then you plot. You use a two-way scatter plot to do it.
Yes.
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 You realize that there's E, F, G, H, I, J, which is not part of the data.
Yeah, they are all blank.
Yes, please.
They are all blank. The reason is because those cells were created in the Excel and they were blank. So you see them as missing data. So how do you resolve it? Go to your Excel file, open the Excel file, and let's resolve. Then we repeat the import again. If you are going to delete this one, but if you don't want to do that, then the best thing is to do this. Please, are you with me?
Yes, Doc.
You can delete them here. Highlight the E to the J here. Highlight them, then you press delete on your keyboard. So we delete all those 6 variables we don't need. Have I made myself clear?
Yes, Doc.
Deleted.
It's deleted, yes. But you can also delete it in the Excel file before you import. So since we have imported this already, delete all those things. We don't need return on investment, annual return on investment, annual return on investment, or you can call return on investment, annual return on investment. So you apply. Then the marketing.
And Doc, are we to leave it double or still floating?
We can make it floating.
Okay.
I think the floating works better for regression. So let's change it to floating. The arrangement has changed, but it's okay once the variables are there. And what's the second one? The second one is marketing. Is that not so?
Yes.
It's marketing.
The second one on yours is marketing.
Marketing. Yeah.
Okay, so what label should we give to marketing?
Marketing expense.
Marketing expenditure.
Yeah.
Marketing expenditure. I think that's it.
Okay.
So marketing expenditure for the label.
Type.
Float.
Let it float. Let it float. Then the salary was it?
What is INT? I see INT there.
Integer.
Okay, so search for it and know the different types of variables that when they are meaning. And next time you come and tell me.
The INT means integer, boss.
Integer, okay.
What's the next variable?
Salaries.
Employee salary.
Staff salaries. Okay, employees.
Employee salaries. Employee, that's what is in this thing. Don't create your own name. Employee salary, that's the label.
Okay.
So let it float. Then RD. You say RD means
Research
what?
and
Someone
development.
gave me the
Research and development.
research and development expenditure. So let's call it research and development expenditure, R&D expenditure. Research and development expenditure. So we change that one to this. Then we apply. Oh, it should be floating, eh?
Yeah.
Apply. Okay, so that's it. So research objective. What's the research objective? Number 1, please read for me very fast.
Determine if R&D expenditure shows diminishing returns, where initial investment yield high return on investment growth, but eventually plateau.
Okay, so that's our research, one of our research objectives. The second one is what?
The model specification. We evaluate whether a standard multiple linear regression, MLR, is appropriate, or if a log transformation of the dependent variable is necessary to satisfy the assumption of normality and homozygosity. Investigate if the relationship between marketing expenditure and return on investment is moderated by the level of employee salaries. So, example, do high-paid sales teams make marketing more effective?
So this could be a research objective for such variables. Then the required task, first of all, we have to do visualization. So how do you do that? We start with the first one. So we plot each of the independent variables against the ROI, the return on investment. So we have 3 graphs. So you can copy them one by one, then you paste it to draw the first one. The second one will draw this one. The third command will draw this one. There's some kind of linear relationship across all of them. Is it correct? From the graph. So here we cannot judge too much because
Doc, on the face of the graph, it appears to be a little linear.
Yes, a little linear, but still we need to do further investigation and determine whether they are all linear. Okay, so you plot each of the independent variables against the dependent variable, and you get these 3 graphs coming out. And we use the word lowest. If you don't add this lowest, it will not draw the red line, which gives you the trend of your scattered plot. It tells you whether the thing is really linear or not. And the red line shows some kind of linearity in our plots. Can we move on? So that's the description. That's what I'm giving here. A quick description of all the 3 graphs. So we can also establish overall linearity using the residuals. So you run the regression, you regress ROI on marketing, salary, and R&D. Then you determine the residual and check the residual plot. Can you see the residual plot here? When the points of the residual plot appear to be scattered around this red line 0, then there's linearity overall linearity in your data. So let's run the residual, this one. After the regression model, run this to determine the residuals. Please, have we finished running? Predict residuals.
Predict residual. A moment.
The residual is the name, and the residual is what you are predicting. So whatever name you want to call that new variable called residual, you type that one first, then residuals.
Prof,
Please, do you understand what I'm trying to say?
25 missing values generated.
In the residuals?
Yes.
First, let's do the regression. Regress the return on investment on marketing, salaries, and R&D. Can you see my command sheet? Then predict the residual. So you see that now it has not written the 25 missing values.
Yes, Doc.
Yeah.
Now
it says variable residual already defined.
So you copy this, paste it in your command window. We are plotting what the variable unit. Please, have you done it?
Yes, Doc.
Great. Are you seeing the result? Is it the same as the one on the screen?
Yes.
Yes, Doc,
Yes,
with a red line.
Great. Great, with the red line.
Yes.
The red line will come if you put this 0. You see the 0 with a bracket at the end.
Oh, okay.
If I put 20 here, it will draw a red line at the 20. But usually the scatter plot should be scattered around the 0. So that's why I drew the red line.
Oh, okay.
So when you delete this 0 here in bracket, you delete it. It will not draw the red line.
Oh, okay.
Are the points scattered around the red line?
Yes, some are dispersed around the red line, but it's
good.
It moves on the path. Or it moves on that path. It appears to be moving on that
But
path.
along the line, it appears it's dispersing.
It's dispersing.
Closer
Exactly.
here, getting here, it is dispersing.
Exactly.
So when there's a U shape, it means the variability is not constant. You see, it's closer here at the beginning to the red line. Getting to the end, it appears to be a U shape, dispersing a little. That it has violated linearity. And when do you say that it has violated the linearity? When you can see some V shape appearing. But when it's scattered uniformly around the red line, then the linearity assumption is intact. So in general, the variables have violated the linearity assumption in our regression. So read it for me.
Okay.
The residual plot in figure 8.8 indicates a violation of the linearity assumption, as the residuals are not randomly scattered around 0. Instead, they display a systematic fan-shaped pattern with increasing spread at higher fitted values, suggesting the presence of non-linearity that the model does not adequately capture.
Okay, so you can see it disperses when you get to higher fitted value. The values are dispersed in the final shape. You can see some kind of final shape. So it means the linearity assumption for the model is violated. So one assumption is violated. So we see how to resolve that problem, that violation. The purpose for this lecture is to show you violation, how to resolve it. That's the main teaching. So I simulate data that at least one or two of assumptions we violated. So that's why I have so many examples here. Each example and the assumption that is violated and what you have to do to rectify it. Can we move on? What about homoscedasticity assumption? Conduct that one. So copy this one, copy this command, e-start, then you paste it, and that will give you the results of the Bruce-Pagan test. We are testing homoscedasticity in our data. What is homoscedasticity? What does it mean? It means the variance in the error term are not constant. The variance in the error term are constant. When they are constant, then we say there is homoscedasticity. When they are not constant, then there's heteroscedasticity. Please, have you pasted this? What's the result?
The result stays constant
variance.
Variance.
H0.
That's the null hypothesis.
Yeah, so the null hypothesis there that the variance is constant. That's homoscedasticity, as in the screen. Yeah. H1 say that the error is not constant. That is heteroscedasticity. So when the p-value is very small, what's the p-value in your what you ran?
0.01.
Good. Because the p-value is small, we reject H0. Rejecting H0 means that the homoscedasticity assumption has been violated. So two assumptions have been violated: linearity assumption and the homoscedasticity assumption also is violated. Remember, we've already generated the residuals. First, we can plot histogram. So copy this, then it will plot this and paste it. It will draw this histogram for you. That's a histogram for the residuals to check normality. Then you can also plot the QQ plot. Please, have you done that?
Yep.
Yes, sir.
Great. So do you have this plot,
Yes,
the graph, the
we have it.
histogram? Great. Then also do the QQ plot for me. Copy this command, paste it, and do the QQ plot for the residuals. So the histogram, does it look like normal distribution? Yes. It's a bell
Yes, it
shape.
does.
It's a bell shape. Please, are you with me?
Yes.
Yeah.
Great. So the histogram looks like a bell shape. It shows normality. And also the QQ plot, the scatter plot also is scattered
Around the line.
Around the line.
around the line.
Yeah.
So also shows signs of
Yeah.
normality. So we do a Shapiro-Wilks test to
Yeah.
confirm these two suspicions that the error terms are normally distributed. That's what we are doing. So we do a Shapiro-Wilks test of the residuals.
And the Shapiro-Wilks test is showing a probability of 0.52719.
0.52719.
Not a, it's a p-value. A p-value of
It's a p-value.
0.5.
52.
Yeah, 0.52719. So
Good. So that's a p-value. A big p-value retains normality. You remember, a big
Yeah.
p-value for the Shapiro-Wilks test retains normality. So the Shapiro-Wilks test confirm normality. The histogram also shows that the data is normally distributed. So the Shapiro-Wilks test becomes a confirmatory test to confirm our suspicion that the error terms are normally distributed.
Yes,
So
please.
how many assumptions have been violated here?
the linearity,
First, the linearity assumption is violated.
The linearity and the homoscedasticity, so 2.
2. But what are the normality? It's been validated. Normality is
Yes,
validated.
please.
Yes.
Validated. The other two are
Yes.
violated.
Yes.
Good. Then we check the fourth one, the multi-collinearity assumption. So the fourth assumption for linear regression. So that's why you can use a VIF instead of plotting the regression. How do you call it? The plot. How do you call that plot? Instead of doing the correlation, you can use the VIF. So just run VIF. Type at your command window VIF. It will do the VIF for you. That's variance. What's the meaning? Variance inflated factor or inflation factor. Please, have you issued a command for VIF?
Yes, please. We
Yes,
see
So
viable
that will give you this. So marketing, what's the VIF for marketing?
Marketing is
1.03.
When the VIF is less than 5, or let's say less than 5, then it means the variance for that variable is not inflated, which means it's good for marketing.
less
So
than
almost all of
absolute
them are the
number
same.
5.
So none of the variable is inflated. Yeah, the absolute number 5, or sometimes we use 10. Some people say 10, but I like using 5. Please, are we okay? So it means all the variables are okay, they are not inflated. So there's no concern for multi-collinearity. So that assumption is validated, it's not violated. So I'm going to generate a logarithmic transformation for all my random variables. So copy this and paste it in your work to generate those random variables. Okay.
Yes, sir.
So you realize that 4 new variables have been created, which are logarithmic transformation of the original variables. Why do we transform them? Because we realize that the linearity assumption for our model has been violated. First, the model 1 is what? The original model where there was no transformation. Let's run that one. Good. Then we look at model 2. Model 1, there was no transformation of any of the variables. In model 2, we transform the R&D. We use the logarithmic transformation of R&D. And for ROI, we use the original variable. Marketing, we use the original variable. Salaries, we use the original variable. For the third model, we maintain marketing, we maintain salaries, but we run the quadratic for the R&D. We run the quadratic for the R&D. So that's the third model. Then we run the fourth model where we find the logarithmic transformation of marketing, salaries, and R&D and maintain the dependent variable to the ROI. We run that model as well. Now, what are the fifth one? Okay, the fifth one, we took the natural log of the dependent variable.
Yes.
Yes.
Then we maintain all the independent variables.
Yes.
Yes.
That's the fifth model.
Yes. Then the fourth, we flipped it.
Then the sixth model, we find the natural log of the dependent variable.
Mm-hmm.
Then the natural log of R&D. That's the sixth model. In our effort to determine the optimal model, you need to run so many of them so that we determine the optimal.
Yes.
What's the seventh model?
The seventh model, we take the natural log of the dependent
all
variable.
The variables, all of them.
All the log.
Both the,
Yeah.
yes, but for both the dependent and the independent variables,
So pay
all of them.
attention to it. Pay attention.
So that's the 7 model. So this is a summary of all the 7 models. That's a summary. So I've generated a summary statistic for all the 7 models. All the R squares are good for all the 7. The R squares are very good. Adjusted R squared are also very good. But which one has the smallest root mean squared? Which of them has the smallest?
The log. Who?
The log full model. Is it this one, the last one?
Yeah.
It has the smallest root mean squared. Which one has the smallest AIC, BIC?
The log
Log.
The log has the smallest AIC, BIC. So it appears in this model, the log is given the optimal model. So that's what I've described here.
Prof, could you take the AIC and BIC again? I'm not thinking
the
log
model with the smallest AIC, BIC is always the best. But you realize that whenever you transform in finance, usually you cannot, when you transform the dependent variable, most of the time automatically it gives you a smallest, how do you call it? It gives you this, it gives you almost a negative AIC and BIC. So usually it's good to compare all the models where you transform the dependent variable, like the 5, 6, and 7 together, and compare the one that you did not transform the dependent variables. You also compare them together. So you realize that these ones are all positive and these ones are all negative. Do you understand what I'm trying to say?
Yes, please, bro.
Great. But
Yes.
in all departments, it depends on sometimes the transformation also depends on your objective.
Prof, I was saying, I think the fifth and sixth one, the fifth and sixth, if you look at their BICs, I'm seeing
Both BIC and AIC.
Mm-hmm. I'm listening to you.
The one asking the question is still online.
No. I'm still online. So what I'm saying is that the AIC for the log linear, that one is 126. So that one
Minus
is that not lower
126.
than minus 126? Or we are considering their negative sign as well in terms of the size?
You are considering the negative. You are considering the negative, not the magnitude.
Okay.
So the lowest is number 7.
Okay, thank you.
So based on the comparative result in table 3, model 7, that's a log full model, is the optimal. So the reason is what I'm giving here. It has the highest R squared. Is that not so? The R squared is the highest, though all of them are good. Though all the R squared are good, the log full model gave us the highest R squared, the lowest root mean squared. The p-value is good for all of them, and the lowest AIC, BIC. So that one is the optimal.
Doc, but what about the adjusted R squared?
It's the same interpretation as the R. The adjusted R squared and the R squared has the same interpretation. The model with the highest adjusted R squared is the best. Then I conducted the Bruce-Pagan test for the log-log. I conducted the Bruce-Pagan test for the log-log. And first I did the residual, that's a graph. Then the Bruce-Pagan test gave us a p-value of what? What's the p-value? How do you conduct the test?
0.3831.
Please, how do you conduct the Bruce-Pagan test? Just after the model, you run the model in Stata, then you give this command. Remember the command I gave you at the top?
Is that something?
E starts then HET test. Just after the test of the log full model, you run this, then it will give you the results for the Bruce-Pagan test. Please, are you with me?
Yes.
What's the answer? What's the p-value for the Bruce-Pagan test?
0.3831.
Yes. So 0.3831 means that you maintain the H naught. H naught said homoscedasticity. And H1 says that heteroscedasticity.
Scedasticity.
Okay. So a big p-value means that the homoscedasticity assumption for the log full model has been validated. So it means the log transformation has solved the problem of homoscedasticity. It has also resolved the problem of linearity. You also plot the linearity curve, and that's what we get. And it has also solved the problem of what? The assumptions that were violated have all been validated now in our new model. Can you see that? So these are the parameters estimation for those new models. That's for our optimal model. That's the parameters. The constant term is what? 1.1332. The coefficient of natural logarithm of R and D is this. And this is that, and that is that. And all their p-values are very small for the estimate. So that is our optimal model. If you want to write the equation, that's the equation. We put this into equation form. So that's the equation. Then if you want to make ROI the subject, you find the exponent of the right-hand side. That makes the ROI the subject. That's if you want to estimate the ROI.
Yes, Prof.
And these are the model interpretation. So you can read through. I think it's very clear and well explained, the interpretation. So you should be able to do it. I said that because it's a log model, the gradients define elasticity. The gradients. We can also conduct statistical inference on the distance. And almost all of them are significant when you conduct them, because all the p-values for all the coefficients are less than what? 0.005. So the inference test shows that all of them are significant. That's what I've done here. Conduct statistical inference for all the estimates. So all of them are significant. Then evaluate the predictive performance. I'm going according to the questions. They say we should evaluate the predictive performance of your model. How do you evaluate that? Yes, I'm listening.
I was thinking with the predictive performance, we will use our model to find an estimate and compare it with the actual observed value.
Exactly so. So you do a comparative analysis between the actual observed values and the predicted value, and see whether the difference between the actual observed value and the actual value and the predicted value, whether there's significant difference between each of them. So when they are very close, then we say that our predictive power of our model is very good.
Permit me to take you just a step back. You stated that for prediction, we do a comparative analysis of the actual values and the observed values. Please.
No, that's a slip of tongue. That's what I said.
Okay.
Actual value and observed values are the same. It's the same term. It's the same term. So we do a comparative analysis between the actual value and the predicted value. The actual observed values for ROI and the predicted value of ROI. We do a comparative analysis.
Okay.
You can even use the pair t-test to do that comparative analysis and check whether there's significant difference between the the observed actual values and the predicted value of your model. So you do that comparative analysis. So sometimes in some models, it's good to do that depending on your objectives.
Okay, that's fine.
Okay, so it's okay. So let's upload the data 8.3.
Let's go to the observation.
It means infrastructure spending.
Okay.
Spending on infrastructure. So copy and paste it as your variable label. Please, are you with me? And let it float. I like the floating variable. Later we'll check the difference between those variables. So we apply. Utility, what does it mean?
Infrastructure spending.
Public utility investment, that's a utility. Public utility investment. Please, are you with me? Public utility investment. Let it float. You apply. Edu. What's the meaning of edu?
Utility.
Education grant.
Investments.
It's in the work, so you can be copying and pasting. Education. Please, you mute your mind. There's echo. I can hear myself from, I don't know.
Good.
So edu is for what? Should we float that one as well? Yes. Then GDP. What does it mean?
Education. Okay.
GDP, what does it mean? Annual gross domestic product growth. Annual GDP growth. Okay. So that's a label. So the dependent variable is GDP growth. The independent variables are X1, X2, X3, which represent infrastructure spending, public utility investment, and education grant, respectively. So what do we want to do? So these are the possible research objectives you can have for this work. Then the task, first of all, you want to do a data analysis and visualization, which I told you how to do it. So we do the baseline model estimation, diagnostic testing. Then addressing multi-collinearity and model range specification. I think we've done all this already, and model selection and final specification. So I've done it already, so you just go through like I've taught you. All of them, all the commands are here. You do the graphs. Please, are you with me?
Yes, sir.
Great. So you do all the 3 graphs, you copy and paste, and it will draw it for you. That if you have imported your data correctly, it will work it out for you. Then here I decide to do the correlation matrix. Please, are you with me?
Yeah.
I decide to do the correlation matrix. Some of the variables are highly correlated. Can you see that?
Yeah. Infra.
No, please, are you listening to me?
Prof, we are listening.
Yes.
Great. The independent variable, when it's highly correlated with the dependent variable, that is okay. That one is not a problem. But independent variable cannot be highly correlated with another independent variable. Like we have here utility and what? Utility and infrastructure. They are highly correlated, almost one.
Yeah.
So there's likely to be a multi-collinearity in this work.
Yeah.
Are you with me?
Yes, sir.
Great. So that you can do the VIF to confirm whether infrastructure and utility are inflated, their variance are inflated. You can check it out. But there's high correlation between the two. And you can see from this graph, pairwise relationship matrix, that there's an almost perfect linearity between what utility and what infrastructure from this diagram here. We call it pairwise relationship matrix. So it is clear. So I have to perform the baseline regression model to conduct my test. So you regress GDP against the other three independent variables. Then you run the residual test. You do the residual test and do the Bruce-Pagan test, this one. So this one will do the residual graph, which is this one. The result is here. And this one will perform the Bruce-Pagan test for you. And the Bruce-Pagan test gives us a p-value of something bigger than 0.05, which implies the validation of what? The homoscedasticity assumption. The homoscedasticity assumption has been validated. Okay? So this assumption is validated from the Bruce-Pagan test. Then we did the normality test. It appears to be normally distributed. And the Shapiro-Wilks test also gave us a very big p-value, which shows that our residuals are what? Normally distributed. The residuals are normally distributed. Then I did the variance inflated factor. And it gave us an average of 171. And you can see utility is inflated. I told you when it's bigger than 10, it means that variable is inflated in your model. It means the estimate of alpha and beta for that variable are inflated. Either they are bigger than the normal estimation or smaller. They are inflated. And the inflation is very high for those two variables. Their standard errors are inflated, the estimations are inflated. So they will not give you a correct value. Why? Because these two variables are highly correlated. Please, are you with me?
Yes, Doc.
So which assumptions have been violated in this study? Number one, I think it's only the multi-collinearity assumption. It's only the multi-collinearity assumption which has been violated.
Yes.
So how do you resolve it? Either you drop one of these, utility or infrastructure, you drop that variable. So your independent variables will be only two. Or you can do a principal component analysis and combine these two variables into one. So first, I decide on the first option. I combine the two. You can add them, infrastructure and utility, to form one variable and use it to run. Or you can drop utility and use only infrastructure, or drop infrastructure and use utility. Okay? So that's what I did there. I find the total, then use it. So that in the long run, we use only two independent variables to run. So we regress the reduced model.
Yes, sir.
In model A, I drop utility. I drop utility and use only infra to run model A. So I drop one of the highly correlated variable. I drop one of them and use only what? Infrastructure to run. And in model B, I use the total of what? The total of infrastructure and what? Utility as one variable to run together with education to run that one. Then model C. What is model C?
You regress total investment.
I regress GDP over total investment.
Yes, and you
From
log
natural
education.
log of education. I took the
Education.
natural log of education. I took the natural logarithm of education. So that will give us model C. Then I run this command. I find this command somewhere where it can give you the comparison of the R squared for all the three models. This one static command that to compare the R squared for you for all the three models. To do the R squared, I think somebody asked me the question earlier, how can you get a table? Is there a command where it can give you the table?
I asked.
Good. I think that's the command I've done for you. Your prayers have been answered.
Thank you.
So this command will give you the comparative table. It will give you all the RMSE, the AIC, the BIC, all of them. One table to compare. So that's my comparative table for all the three models. Which one has the highest R squared?
B.
Model A.
B.
Model C.
B.
Actually,
No,
model C.
model
C.
Model C.
Model C.
Model C.
Okay.
Model
So
C.
Yeah, the
stop rushing,
highest R
Solo.
squared. That model C. What are adjusted R squared? Which one is the highest?
Still model C.
Model C.
Same.
And which one gives us the lowest root mean squared?
Model
Same.
C.
Model C.
Same.
So C is topping. Which one gives us the smallest AIC?
Model C.
Same. Yeah.
And
Same.
BIC also. So in all departments, model C give us the optimal model. What's the model C anyway? Model C is when we regress GDP against total investment when we add the two highly correlated
natural log education.
And natural log education.
Yes, please.
That one gave us the optimal model.
Yes.
That one gave us the optimal model. So once that you get the optimal model, you zero in on that. Okay. You zero in on that and continue with that model. You neglect all the others. Yeah, Adams.
Prof, please, is there any situation where R square and maybe adjusted R square will give you the highest, but the root mean square is also giving you the highest instead of the lowest? And in that case, which one do we base on your decision to pick?
That's one of the confusion. But when it happens that way, I depend only on the BIC and the AIC.
Okay. Thank you.
When it happens that way, I depend only on the AIC and the BIC because that is an advanced way of checking the fitness of a model.
Okay.
That's the Archimedes information criterion.
The archaic and the Bayesian information criteria. Archaic. Is that how you pronounce it?
Yes, sir.
Yes,
archaic information criteria. That's for AIC. And BIC, Bayesian information criteria. And usually when like IK is high, Bayesian also be high. When it's low, this one also be low. So those two are more reliable in doing comparative analysis than the R squared and the root mean squared. But it's very rare to have it that way. In most cases, they all give the same results. They all point to one model as the optimal in most cases. And look at the variance inflation for them. They almost one, which is very good. I told you when it's less than 5, it means all the variables are not inflated. It means the estimates are very good. They are not inflated. Are you with me?
Yes, sir.
Yes, sir.
So let me take you back and ask you a question.
Okay.
I want to find out the reason why you created a log for education. Is it because you also created a composite variables for infra and utility so that it can match them?
No, not that. Not that. Sometimes it's just a matter of try and error. After finding that there is a multi-collinearity, and for that matter, the first model we dropped. Model A, we dropped what? What do we drop? Utility. We drop utility because utility is highly correlated with our infrastructure. So we drop utility. So I decided also model B to combine utility and infrastructure to form a new variable called total investment. Are you getting me? So I work out that one. So in my curiosity, I say, oh, why don't I try logarithm of education and see whether I can beat these two models? And truly, to my expectation, to my surprise, model C beat model A and B. So sometimes in PhD, sometimes you do a lot of try and error and see which of the models will give us the optimal.
Okay, so I asked that
because more especially the linearity assumption was not violated. Usually we do transformation when the linearity assumption is violated. But in this case, it was not violated because when you look at this plot, it's like it's not V shape, it's not funnel shape. Usually when this plot is a funnel shape, it's dispersing. Then we say the linearity assumption has been violated. But it was not violated, so there's no reason to do logarithm transformation of education. But here I decided to give it a try, and that gave me the optimal model. Have I answered your question?
Yes. But
are you okay, or your hands are still up?
No, that is okay, but because I thought
he's asking me, my brother. The question is to me. I was okay until I think the last person's answer you gave. That we use the natural log to convert. That is my understanding, to convert a non-linear relationship into a linear one. So it means that we are transforming the data or the variable. In doing so, are we not manipulating the data
we are not manipulating.
To be linear?
Log transformation is not manipulation. It's a legal manipulation. Let's call it that way. It's a manipulation which is legal in research. But sometimes you can do illegal manipulation of data.
Prof. And then to add to what Prof said, Prof, I believe that even with as you said, legal manipulation, when you are done, you still test the efficiency of the model by comparing it with the actual observed values.
Exactly.
So if you compare it with the actual observed values and it's similar, then it means you've not violated
to the actual observed, it is valid.
It's valid. You've not really
I told that next time when we meet, I may get you the status command I use. because I have not displayed it on this slide. I'll get you the stator command for computing the predicted values and compare them with what?
The observed values.
The observed values, and see whether there are significant differences between the predicted and the observed pairwise. If the difference is not significant, you can conduct the pair t-test I taught you last week to check whether there's significant difference between the observed and the predicted. If there's no significant difference, it means your model specification is very good.
Hello, Prof.
Yes, I'm listening.
So as you were discussing with or let me say, addressing the questions, I took it upon myself to go back and then run Model C, this time without the natural log of education. And
Okay.
when I did that, after that, I generated the table that has the adjusted R square, the BIC, and the AIC. And I realized that the values for Model D and then Model C are the same. So I think what it means is that the composite variable solve the issue. Yeah, so even if you didn't take the natural log of education, it will still be Model C.
Model C is where we took the natural log of education. Is that not
Yes,
so?
so what I did was Model D. I generated for Model D, and
you generated for Model D where you did what?
Where I did not take the natural log of
You
education.
didn't take the natural log.
Okay, but I think that model is already there.
No.
Where we had the total and we did not, this that Model B. We had the total, but we did not take the natural log of education.
Oh, okay.
That's B.
Okay, Prof.
So that model is already there.
And then I'm young, Solo with intro. Hey.
Solo, concentrate. Solo, no, you're slowing us down.
Stop disturbing.
Okay, so it's almost 5. So I'll give you the reasons here.
5 already.
Yeah, it's 5 already. So it's 3
past
hours.
5.
But we started after 5, so it's less than 3 hours.
Mathematicians.
But
So
so
all that
join is only 5, Prof.
Please, are you listening? So all that I'll
Yes, sir.
explain is what I'll give in model selection. Which one do you select? So model C happens to have the variance inflated have reduced from 257. You remember for infrastructure, it has reduced to 1. Then the non-linearity corrected. Was there non-linearity? The non-linearity is corrected in model C. I can't remember that there was non-linearity. Was there non-linearity? This
No,
one,
it
does it
was
look
in
like
the DNF.
does it look like non-linear? You look at the residual plot for non-linearity. What was the conclusion?
Well, initially,
And the linearity assumption of the model. So it confirms the homoscedasticity and the linearity assumption. So there was nothing like violation of the linearity assumption. They were both validated.
But may I remind you that you said something like when we observe the scatter plot, we could see that they are not so close to the line. There's been some spreading around.
Some spreading.
Yeah, so
maybe that's a suspicion because that's a problem of scatter plot. It's not a test. So sometimes it depends on the eyes of the beholder, the one who is looking at it. Someone will say that it's scattered, someone will say that it's close. Do you understand? Because it's not a test. So that's why I think because I'm not too sure. Please, are you listening?
Yes.
Because I was not too sure which conclusion to draw based on the scatter plot here. That's why I log on the education to run. Please, are you with me?
Yes.
I log on the education to run it. And that one happens to be the optimal model. That one happens to be the optimal model. So selection of optimal model. Please, are you with me?
Yes.
So for the
So
final regression equation, etc., everything has been written nicely. Then the interpretation, now I wrote the coefficient of the optimal model. So you don't need to write all the coefficients because you don't know which one you are going to use. So when you get the optimal model, then you write that coefficient and their p-values, their confidence interval, the t-values, standard errors, etc. Then you can write down the equation and do the interpretation of the coefficients and the inferences, the statistical inferences of the precision and all those things. Assessment of model fit, everything has been done. Are you okay? Any question, please? Otherwise, we finish for the day.